In probability theory and information theory, the mutual information or transinformation of two random variables is a measure of the variables' mutual dependence. The most common unit of measurement of mutual information is the bit. Definition of mutual information: formally, the mutual information of two discrete random variables x and y can be defined as where p, x, y, is the joint probability distribution function of x and y, and under the marginal probability distribution functions of x and y respectively. In the case of continuous random variables, the summation is replaced by a definite double integral, where p, x, y, is now the joint probability density function of x and y, and under the marginal probability density functions of x and y respectively. If the log base 2 is used, the units of mutual information are the bit. Intuitively, mutual information measures the information that x and y share. It measures how much knowing one of these variables reduces uncertainty about the other. For example, if x and y are independent, then knowing x does not give any information about y and vice versa, so their mutual information is zero. At the other extreme, if x is a deterministic function of y and y is a deterministic function of x, then all information conveyed by x is shared with y. Knowing x determines the value of y and vice versa. As a result, in this case the mutual information is the same as the uncertainty contained in y alone, namely the entropy of y. Moreover, this mutual information is the same as the entropy of x and is the entropy of y. Mutual information is a measure of the inherent dependence expressed in the joint distribution of x and y relative to the joint distribution of x and y under the assumption of independence. Mutual information therefore measures dependence in the following sense: I, x, y, equals 0 if and only if x and y are independent random variables. This is easy to see in one direction: if x and y are independent, then p, x, y, equals p, x, p, y, and therefore. Moreover, mutual information is non-negative EL permil beta 0. See below, and symmetric equals I, y, x. Relation to other quantities, mutual information can be equivalently expressed as where under the marginal entropies, h, xy, and h, yx, are the conditional entropies, and h, x, y, is the joint entropy of x and y. Using Jensen's inequality on the definition of mutual information, we can show that I, x, y, is non-negative. Consequently, intuitively, if entropy h, x, is regarded as a measure of uncertainty about a random variable, then h, x, y, is a measure of what y does not say about x. This is the amount of uncertainty remaining about x after y is known, and thus the right side of the first of these equalities can be read as the amount of uncertainty in x, minus the amount of uncertainty in x which remains after y is known, which is equivalent to the amount of uncertainty in x which is removed by knowing y. This corroborates the intuitive meaning of mutual information as the amount of information that knowing either variable provides about the other. Note that in the discrete case h, x, x, equals 0 and therefore h, x, equals I, x, x. Thus I, x, x, a per million I, x, y, and one can formulate the basic principle that a variable contains at least as much information about itself as any other variable can provide. Mutual information can also be expressed as a Kullbacher-Euro-Leibler divergence of the product p, x, a, p, y, of the marginal distributions of the two random variables x and y, from p, x, y, the random variables' joint distribution. Furthermore, let p, x, y, equals p, x, y, slash p, y. Then, note that here, the Kullbacher-Leibler divergence is calculated over the random variable x only, and the expression is now a random variable, because of the dependence on y. Thus mutual information can also be understood as the expectation of the Kullbacher-Euro-Leibler divergence of the univariate distribution p, x, of x from the conditional distribution p, x, y, of x given y. The more different the distributions p, x, y, and p, x, are on average, the greater the information gain. Variations of mutual information. Several variations on mutual information have been proposed to suit various needs. Among these are normalized variants and generalizations to more than two variables. Metric. Many applications require a metric, that is, a distance measure between points. The quantity satisfies the properties of a metric. This distance metric is also known as the variation of information. If a discrete random variables, then all the entropy terms are non-negative, so and one can define a normalized distance. The metric d is a universal metric, in that if any other distance measure places x and y close by, then the d will also judge them close. A set-theoretic interpretation of information shows that, which is effectively the jagged distance between x and y, conditional mutual information. Sometimes it is useful to express the mutual information of two random variables conditioned on a third, which can be simplified as: conditioning on a third random variable may either increase or decrease the mutual information, but it is always true that, for discrete, jointly distributed random variables x, y, z, this result has been used as a basic building block for proving other inequalities in information theory. Multivariate mutual information. Several generalizations of mutual information to more than two random variables have been proposed, such as total correlation and interaction information. If Shannon entropy is viewed as a signed measure in the context of information diagrams, as explained in the article Information Theory and Measure Theory, then the only definition of multivariate mutual information that makes sense is as follows. And for where we define, this definition of multivariate mutual information is identical to that of interaction information except for a change in sign when the number of random variables is odd. If and are two sets of variables, then the mutual information between them is. Applications. Applying information diagrams blindly to derive the above definition has been criticized, and indeed it has found rather limited practical application, since it is difficult to visualize or grasp the significance of this quantity for a large number of random variables. It can be zero, positive, or negative for any one high-dimensional generalization scheme which maximizes the mutual information between the joint distribution and other target variables is found to be useful in feature selection. Mutual information is also used in the area of signal processing as a measure of similarity between two signals. For example, FMI metric is an image fusion performance measure that makes use of mutual information in order to measure the amount of information that the fused image contains about the source images. The MATLAB code for this metric can be found at normalized variance. Normalized variants of the mutual information are provided by the coefficients of constraint, uncertainty coefficient or proficiency. The two coefficients are not necessarily equal. In some cases a symmetric measure may be desired, such as the following redundancy measure, which attains a minimum of 0 when the variables are independent and a maximum value of when one variable becomes completely redundant with the knowledge of the other. See also redundancy. Another symmetrical measure is the symmetric uncertainty, given by which represents a weighted average of the two uncertainty coefficients. If we consider mutual information as a special case of the total correlation or dual total correlation, the normalized versions are respectively, and other normalized versions are provided by the following expressions. The quantity is a metric, that is satisfies the triangle inequality, etc. Weighted variance, in the traditional formulation of the mutual information, each event or object specified by is weighted by the corresponding probability. This assumes that all objects or events are equivalent apart from their probability of occurrence. However, in some applications it may be the case that certain objects or events are more significant than others, or that certain patterns of association are more semantically important than others. For example, the deterministic mapping may be viewed as stronger than the deterministic mapping, although these relationships would yield the same mutual information. This is because the mutual information is not sensitive at all to any inherent ordering in the variable values, and is therefore not sensitive at all to the form of the relational mapping between the associated variables. If it is desired that the former relation showing agreement on all variable values be judged stronger than the later relation, then it is possible to use the following weighted mutual information, which places a weight on the probability of each variable value co-occurrence. This allows that certain probabilities may carry more or less significance than others, thereby allowing the quantification of relevant holistic or pro-occurrence factors. In the above example, using larger relative weights for, and would have the effect of assessing greater informativeness for the relation than for the relation, which may be desirable in some cases of pattern recognition, and the like. This weighted mutual information is a form of weighted KL divergence, which is known to take negative values for some inputs, and there are examples where the weighted mutual information also takes negative values. Adjusted mutual information. A probability distribution can be viewed as a partition of a set. One may then ask, if a set were partitioned randomly, what would the distribution of probabilities be? What would the expectation value of the mutual information be? The adjusted mutual information or AMI subtracts the expectation value of the MI, so that the AMI is 0 when two different distributions are random, and 1 when two distributions are identical. The AMI is defined in analogy to the adjusted RAND index of two different partitions of a set. Absolute mutual information. Using the ideas of Kolmogorov complexity, one can consider the mutual information of two sequences independent of any probability distribution. To establish that this quantity is symmetric up to a logarithmic factor requires the chain rule for Kolmogorov complexity. Approximations of this quantity via compression can be used to define a distance measure to perform a hierarchical clustering of sequences without having any domain knowledge of the sequences. Mutual information for discrete data. When X and Y are limited to be in a discrete number of states, observation data is summarized in a contingency table, with row variable X and column variable Y. Mutual information is one of the measures of association or correlation between the row and column variables. Other measures of association include Pearson's chi-squared test statistics, G-test statistics, etc. In fact, mutual information is equal to G-test statistics divided by 2n, where n is the sample size. In the special case where the number of states for both row and column variables is 2, the degrees of freedom of the Pearson's chi-squared test is 1. Out of the 4 terms in the summation, only one is independent. It is the reason that mutual information function has an exact relationship with the correlation function for binary sequences. Applications of mutual information. In many applications, one wants to maximize mutual information, which is often equivalent to minimizing conditional entropy. Examples include, in search engine technology, mutual information between phrases and contexts is used as a feature for k-means clustering to discover semantic clusters. In telecommunications, the channel capacity is equal to the mutual information, maximized over all input distributions. Discriminative training procedures for hidden Markov models have been proposed based on the maximum mutual information criterion. RNA secondary structure prediction from a multiple sequence alignment. Phylogenetic profiling prediction from pairwise present and disappearance of functionally linked genes. Mutual information has been used as a criterion for feature selection and feature transformations in machine learning. It can be used to characterize both the relevance and redundancy of variables, such as the minimum redundancy feature selection. Mutual information is used in determining the similarity of two different clusterings of a data set. As such, it provides some advantages over the traditional RAND index. Mutual information of words is often used as a significance function for the computation of collocations in corpus linguistics. This has the added complexity that no word instance is an instance to two different words. Rather, one counts instances where two words occur adjacent or in close proximity. This slightly complicates the calculation, since the expected probability of one word occurring within n words of another goes up with n. Mutual information is used in medical imaging for image registration. Given a reference image, and a second image which needs to be put into the same coordinate system as the reference image, this image is deformed until the mutual information between it and the reference image is maximized. detection of phase synchronization in time series analysis, in the Infomax method for neural net and other machine learning, including the Infomax-based independent component analysis algorithm. Average mutual information in delay embedding theorem is used for determining the embedding delay parameter. Mutual information between genes in expression microarray data is used by the Arachne algorithm for reconstruction of gene networks. In statistical mechanics, Loschmidt's paradox may be expressed in terms of mutual information. Loschmidt noted that it must be impossible to determine a physical law which lacks time reversal symmetry only from physical laws which have this symmetry. He pointed out that the H-theorem of Boltzmann made the assumption that the velocities of particles in a gas were permanently uncorrelated, which removed the time symmetry inherent in the H-theorem. It can be shown that if a system is described by a probability density in phase space, then Liouville's theorem implies that the joint information of the distribution remains constant in time. The joint information is equal to the mutual information plus the sum of all the marginal information for each particle coordinate. Boltzmann's assumption amounts to ignoring the mutual information in the calculation of entropy, which yields the thermodynamic entropy. The mutual information is used to learn the structure of Bayesian networks, dynamic Bayesian networks, which explain the causal relationship between random variables, as exemplified by the Global MIT toolkit. 2. Learning the globally optimal dynamic Bayesian network with the mutual information test criterion. Popular cost function in decision tree learning. See also, pointwise mutual information, quantum mutual information, notes, Alexander Kraskov, Harold Station Paragraph Bauer, Ralph G. Andzijak, and Peter Grasberger, Hierarchical Clustering Based on Mutual Information, AR-ZIV Q-Bio/0311-039, Christopher D. Manning, Prabhakar Raghavan, Hinrich Shawan-Cortazar. An Introduction to Information Retrieval. Cambridge University Press. ISBN A0-521-86571-9. Halifat, MBA, Aghalzadeh, A., and Sirad Arabi, H.A. Non-reference image fusion metric based on mutual information of image features. Computers and Electrical Engineering, 37, 5, 744-756. http www.mathworks.compiler exchange/45926 Feature Mutual Information fMI Image Fusion Metric, Coombs, C.H., Dawes, R.M. and Tversky, A. Mathematical Psychology, An Elementary Introduction. Englewood Cliffs, New Jersey, Prentice Hall A., A.B. Press, W.H. Tucholsky, S.A. Vettling, W.T. Flannery, B.P. Section 14.7.3. Conditional Entropy and Mutual Information. Numerical Recipes, The Art of Scientific Computing. New York, Cambridge University Press. ISBN A978-0-521-88068-8. White, Jim. Steingold, Sam. Fornell, Connie. Performance Metrics for Group Detection Algorithms. Interface 2004, Yao, YY Information Theoretic Measures for Knowledge Discovery and Data Mining. In Kamshu. Entropy Measures, Maximum Entropy Principle and Emerging Applications. Springer PPA 115 Euro 136 Strel, Alexander. Joy de Poche. Cluster Ensembles Euro a Knowledge Reuse Framework for Combining Multiple Partitions. Journal of Machine Learning Research 3, 583 Euro 617 doi, 10.116/15324430332189775 Vin, Nguyen Xuan. Epps, Julian. Bailey, James, Information Theoretic Measures for Clusterings Comparison, Variance, Properties, Normalization and Correction for Chance, The Journal of Machine Learning Research 11, 2837 Euro 54 GVINLSETH, TO The Relative Useful Information Measure, Some Comments. Information Sciences, 56, 1, 35-38. Pocock, a feature selection viaduct joint likelihood or, Wench and Lee. Mutual information functions versus correlation functions. JSTAT. Phase 60, 823 Euro 837 doi, 10.1007/BF010259996 1. Parsing a Natural Language Using Mutual Information Statistics by David M. Magerman and Mitchell P. Marcus, Hugh Everett Theory of the Universal Wave Function, Thesis, Princeton University pages 1 Euro 140, Hugh Everett, Relative State Formulation of Quantum Mechanics, Reviews of Modern Physics Vol 29, pages 454 Euro 462. References, Sila-Brorsi, R. Paul Viton E. Clustering by Compression. IEEE Transactions on Information Theory 51, 1523 Euro 1545. doi, 10.1109/tit. 2005.844059 Cronbach L.J. on the Non-Rational Application of Information Measures in Psychology, in Henry Quisler, ed., Information Theory in Psychology, Problems and Methods, Free Press, Glencoe, Illinois, ppA 14 Euro 30. Church, Kenneth Ward. Hanks, Patrick. Word Association Norms, Mutual Information, and Lexicography. Proceedings of the 27th Annual Meeting of the Association for Computational Linguistics are, Gayasu, Silverou. Information Theory with Applications. McGraw-Hill, New York. ISBN A978-0070251090 Lee, Ming. Paul Viton E. An Introduction to Kolmogorov Complexity and Its Applications. New York, Springer Verlag. ISBN A0-387-94868-6 Lockhead GR Identification and the Form of Multidimensional Discrimination Space, Journal of Experimental Psychology 85, 1 Euro 10. David J. C. Mackay. Information Theory, Inference, and Learning Algorithms Cambridge, Cambridge University Press, 2003. ISBN 0-521-64298-1, Hawifhat, MBA, Aghalzadeh, A., and Siradarabi, H.A. Non-reference image fusion metric based on mutual information of image features. Computers and Electrical Engineering, 37, 5, 744-756. Athanasios Papoulis. Probability, Random Variables, and Stochastic Processes, 2nd edition. New York, McGraw-Hill, 1984. Witten, Ian H. and Frank, Ibe. Data Mining, Practical Machine Learning Tools and Techniques. Morgan Kaufmann, Amsterdam. ISBN A978-0-12-374856-0, Peng, H.C., Long, F., and Ding, C. Feature selection based on mutual information, criteria of max dependency, max relevance, and min redundancy. IEEE Transactions on Pattern Analysis and Machine Intelligence 27, 1226 Euro 1238. doi, 10.1109/TPAMI. 2005.159 Andreas Ribeiro, Stuart A. Kaufman, Jason Lloyd Price, Bjorn Samuelson, and Joshua Sokola. Mutual Information in Random Boolean Models of Regulatory Networks. Physical Review E77. AR-Ziv, 0707.3642 Wells, W.M. 3. Viola, P., Atsumi, H., Nakajima, S., Kikinis, on multimodal volume registration by maximization of mutual information. Medical Image Analysis 1, 35 Euro 51 doi, 10.1016 per second 1361-8415, 01, 80004-9. PMIDA 9873920A.